Welcome to the morning session, and the first speaker is Ajay Chandra from Imperial, and he'll give us the first part of the talk with Yvan René on renormalization and regularity structures. Please.
All right, thanks for the introduction, and thanks to the organizers for giving me the opportunity to speak. So my goals for this talk are to communicate some of the main ideas of the theory of regularity structures and the more recent developments that have led this to, that have kind of completed the picture so that now we have a robust local existence theory for a wide class of singular SPD that's fully automated. And so again, so the work that I'm describing involves Yvan Brunet, Ilya Sheverev, Martin Heirer, and Lorenzo Zamboni. All right. So let's start by talking about the scope. So what is an example of a singular SPD? So this isn't the most general type of SPD we can treat, but it's a kind of good place to start. So we're going to solve a local existence problem. So what you want to imagine is we're in some finite region of space-time. So here I've chosen the d-dimensional torus, and we're also expecting to find solutions local in time. So we're allowing for the possibility of finite time blow-up. And so here I've put the kind of form of equation we're trying to solve. So you should think about the solution formally as some function from our compact space-time region to R, but in practice it's actually going to be a distribution. And what are the main features that we want in the types of equations that we apply this theory to? Well, what we expect is that there's going to be, in the cases we're interested in, there's going to be a rough driving term, which is what causes a lot of the difficulty in this theory. And so here, all you need to assume is that it's a rough, stationary, generalized random field. So for instance, space-time white noise. So we can work in the setting more general than space-time white noise. It doesn't have to be Gaussian. And then the other important part of the story here is that we need if you look at this L, this should be a differential operator on space. So for instance, take the Laplacian, and what we want is the Green's function, or the inverse differential operator, to be regularizing. Okay, so these are kind of some of the key properties of the equations that we're going to be talking about. And then another important condition, so if you remove this nonlinearity, then it just becomes a linear equation. So our whole approach is a perturbative approach of understanding how to perturb around the linear equation. And there's a requirement on this nonlinearity, which is that somehow its effect diminishes as you go to smaller and smaller scales. So in singular SPD, this is called subcriticality. In field theory, this would be called super renormalizability. And so the obstacle for a singular SPD, or why you need to invent new stuff, is that this equation is not something that is posed on any sort of classical space of functions or distributions. In particular, so if you just if you think about the solution as being a P, this inverse differential operator applied to the right-hand side, you expect that the solution isn't going to be any better than this term. So this is just a solution to the linear equation. But in many cases of interest, or what will happen is that this thing will be so rough that it lives in a space where we don't have a canonical definition of the nonlinearity. So for instance, it could be a distribution, and this could be some sort of pointwise product. So, okay, so there's more non-trivial stuff going on here. So in practice, understanding how to give meaning to this equation requires us to implement some sort of renormalization. And so I'll quickly go over that, but the way that you intuitively understand the need for renormalization first is to look at kind of formal perturbation theory and understand where individual terms diverge. But then after we understand how to renormalize, the kind of real analysis problem is, so the perturbative expansions you use to kind of understand divergences when you're starting out are uncontrollable, the infinite series that are non-summable. And so then the game is to somehow develop a kind of partial expansion which we can control, which allows us to see enough structure in order to see renormalization cancellations, but is still something that we can keep under control. So I'll try to describe both of these aspects now. Okay, so first let's quickly go over the purely perturbative approach to these equations, just in case you haven't seen it before. And I'm going to specialize to the case of the stochastic quantization equation for 543. So here we're in 3 dimensions and the noise is space-time white noise. Okay. So, so this equation as it is right now, of course, it won't make any sense because you expect the field to live in a space of distributions and you won't be able to define this product. So how you can get a meaningful equation is you can regularize, right? So you can just mollify the driving noise with some smooth mollifier, and I associate some length scale to the mollifier, epsilon. And as epsilon goes to 0, you should think about this as converging to a delta function. Okay, so now you can solve this equation, but you won't proceed until you understand how to renormalize, because the solutions you get to this smooth problem will fail to converge to a non-trivial limit as epsilon goes to 0. And so the perturbative expansion will show you a little bit of what's going on. So in order to go to the perturbative expansion, it's good to rewrite, or I find it helpful to just go to rewrite the equation as an integral fixed point equation. And so then we can generate perturbation theory. So in field theory, you generate perturbation theory by expanding an exponential. Here we generate it by iterating a fixed point problem. And so let's just start with the guess of the solution is equal to 0. Then if I plug that in, I'm going to start getting terms. I'm introducing some graphical notation. So a single dot represents an occurrence of space-time white noise, and the epsilon tells me that it's been regularized. And then I draw a vertical line below to indicate the action of P, right? So this lollipop is just P applied to this noise. And the epsilon there is just to remind us that the noise in that tree has been regularized. And so if I keep going in this expansion, so here we're beginning to see more complicated objects. So when I join multiple trees at the root, that just corresponds to pointwise multiplication in space-time. Okay? With this graphical notation, we have a nice kind of way of writing all the trees that we get. Okay, so obviously there's some kind of clear combinatorial patterns going on here. So you can kind of think about these as sort of the analogs of Feynman graphs. But they're a little bit different than Feynman graphs because they don't represent contributions to correlation functions, but they're actually random fields, right? So these are all representing multilinear functionals of the driving noise. But like Feynman diagrams, they have convergence issues as you remove the ultraviolet cutoff. So many of these random fields will not converge. So when I talk about these trees converging, I'm talking about the convergence of random fields, okay? But many of these will not converge, and you can isolate the issue to the diverging expectations of two random fields that sort of appear as subtrees in many of these trees. And so here, maybe I'll just quickly, so this guy, the cherry. So I said it's the expectation of this that creates a problem. So when you take the expectation of this, so I'm in the stationary case, so I can evaluate things at 0. It doesn't matter here. Then, if you just, this is just a Gaussian random variable, which is delta correlated. So if I take the expectation, these two things are forced to live at the same space-time point. And so here, if I kind of continue using the same graphical notation, this thing actually represents a real Feynman graph, which is just a tadpole. So the first symbol here corresponds to this tadpole renormalization or Wick renormalization. And then the second term, the expectation of the second term includes a contraction that corresponds to the sunset diagram or the non-trivial mass renormalization. Okay? So the story, and you can kind of do calculations to show that these actually correspond to the renormalizations that you would do in the case for 543, the static problem. Okay. So these renormalize, if you want to cancel these expectations, the expectations of these subtrees when they appear in larger trees, then that guides you into how to choose counter terms into the renormalized equation. Okay. So here you can see that there is so this C incorporates these expectations, and it's multiplying a field because you can kind of see that you're sort of missing a line here, right? So that's how you can see the shape of the counter term. All right.
Ajay, is it easy to see why the counter terms are the same as in the static case?
Yeah, I mean, if you kind of use, you just use identities about integrating the heat kernel and getting inverse Laplacians. Yeah, so you could turn it into a theorem, I think, yeah. There's some kind of maybe issues with how you, sometimes you have to truncate the heat kernel. This could cause some technical issues, but yeah, morally it's kind of definitely very clear. Okay, any other questions? Okay, so so as I said before, so you see, so we have this infinite tree expansion. Sometimes, you may think trees can't be that bad. So why can't we control a full expansion into trees? Well, these are stochastic objects, and if you start looking at their convergence, you'll want to maybe do some kind of Wiener chaos expansion to see the convergence in various chaoses, and then you'll see graphs appear, right? So this is kind of similar to the issue of that you can't control the sum over all connected graphs. So we need to do a different sort of expansion. And so the regularity structures approach is to look for the solution to this SPDE. So it's going to kind of take maybe think in terms more of a type of kind of new PDE theory, and it's going to say, okay, I'm going to instead limit myself to looking for solutions in a space of special distributions where I assume that these special distributions have good local expansions in terms of those trees that I just described. Okay, and so we're going to actually have to describe a little bit what those expansions are, but that will come next. Let me just say now that you should think about these expansions as generalizing Taylor series. And then if we go back to the issues that the obstacle I described earlier, the key benefit or the win here is that somehow via these local expansions, I'm going to be able to think about distributions that were classically rough as having good regularity, right? So really, regularity we're generalizing regularity beyond something that I can approximate with polynomials to just something I can approximate with things that I can understand. Okay, so now I want to just quickly go over classical Holder spaces to give a flavor, to communicate what you want from these sorts of expansions, okay? So let's just fix some n, some non-negative integer, and pick a regularity exponent between n and n plus 1. And so I just want to think a little bit about about C alpha functions, so alpha Holder functions. And so one way to think about the condition of being alpha Holder is that this function admits good polynomial approximations at each space-time point. So the condition of being alpha Holder when alpha is between n and n plus 1 is that at each point I can find a Taylor expansion that approximates the function up to order alpha. So here I'm just going to dress that up a bit, and I'm going to associate to every C alpha function this jet, so this family of Taylor polynomials that I have at each point. And so here I've kind of used an abstract notation, but this is just a way of storing the Taylor series. So this is just the Taylor series based at point x, and these are nothing but the derivatives of the function evaluated at x. And these x to the j's, you should think about them as just computing algebraic indeterminates that I'm using just to help me store data in various places. So if I want to actually use this sort of abstract jet in order to approximate a function near a base point x, well, at some argument, well, what I want to do is I want to take this jet and I want to replace every occurrence of x with just argument minus x, right? That's just turning an abstract sort of Taylor series into an honest Taylor series. Okay. So now let's actually forget about the function and then let's look at the jet. So if I forget about this function, just hand you something like this, what is some sort of sanity check that you could apply to tell you that this jet is somehow, it's a family of local approximations to some object that really exists? Well, what you want to do is you want to look at how this thing depends as you move the base point. Now, so here to kind of give the criterion that will tell us that a jet is actually a family of local approximations, what you want to do is kind of introduce a base point, a change of base point map, which you should think of as taking an expansion centered at x prime and then moving around these monomials so that I can evaluate it at x, right? So, okay, so if you think about this, this is basically just fixing the issue with trying to apply this definition with different base points. And so if I define this map like this and then extend it multiplicatively to these powers, then one thing you can do is you can look at the jet at one point and then look at the jet at another point, use the parallel transport or this change of base point map to move it to the first point and look at the difference, okay? And so then you'll get another linear combination of these x to the j's. All right. And so, okay, so who are these guys? Well, it's a calculus 1 exercise in the case where this thing actually came from a function. If this is the jet of a function, then these CJs are just Taylor remainders. It's the Taylor remainder of the derivative of order n minus j centered around this x prime point and evaluated at x. Okay, and so maybe the first thing to convince yourself is this holds when j equals 0. All right. So here by Taylor remainder, I mean you're evaluating this at x, and then you're subtracting from that the Taylor expansion of this guy centered at x prime evaluated at x. And so what is a good criterion, or a criterion that works? It's that this should vanish at some order. which is x minus x prime alpha to the power alpha minus j. And if you plug in j equals 0, that's precisely the condition that I described before for what it means to be a C alpha function. This is strict so for the case of classical Holder functions, this seems like too much information. So why are you interested if you know that you can approximate a function with a Taylor polynomial? It doesn't tell you that much more that you can approximate its derivative with a lower order Taylor polynomial. But when we generalize to the case where we allow non-classical monomials, so when we start allowing trees in this expansion, it turns out that including a little bit, requiring this at all orders, not just the lowest order, is the right one. And this will guarantee that someone can hand us an expansion, and then we'll be able to reconstruct this family of local expansions into the object that is described by that family. Okay. So the jet, so this should be a phi. So the form of the jet of the solution to the phi 4-3 equation, so I'm using lowercase for the actual function and uppercase for this abstract jet, is going to look something like this. And so I'm using z to represent the kind of space-time polynomials. So these j's are actually multi-indices. And the trees are kind of placeholders for the trees that we saw before. So you should think about these trees as actually algebraic objects that, that I'm going to use to populate these jets. And so, okay, so we have a new space of monomials in these jets, as I just described. One important notion that you have for polynomials that you should have here also is a notion of degree. And so the way that we're going to define degree is, so the measure of degree is going to tell us how a monomial behaves when you evaluate it near a base point. So what we're going to do is we're going to set the degree of the noise to -5/2, which is, okay, -5/2 just came out of nowhere, but you should think about it as a quantitative measure of the blow-up of the space-time white noise. And then we'll enforce that if you drop a vertical line below a tree or hit it with P, then the degree increases by 2. So this is a quantitative statement about the regularization of that inverse differential operator that I kind of gave as an assumption before. And then we're going to enforce that the degree of the product of monomials is equal to the sum of the degrees of the individual monomials. Okay, so here, okay, we're not allowing for kind of any anomalous scaling in this sort of thing. Okay. So this is just, so here I've just described a framework where you have jets taking values and linear combinations of abstract objects, and I gave you some notion of degree for these abstract objects. But in order to start making these things work like the classical Taylor expansions, we need to give them life with something called a model. And so a model, Z, consists of two families of objects. The first one is a family of maps parameterized by space-time points. And so this space-time point, this pi z, takes one of these monomials, these abstract monomials, and makes it a concrete analytic object centered about z. So this gives, in some sense, this map acting on these blue symbols is the analog of this correspondence, of taking an abstract monomial and looking at its kind of incarnation centered about a point.
So the degree, is it good to think of it as minus the scaling dimension in field theoretic sense?
Yes, yeah, I think so. Yeah, like parabolic scaling dimension. Yeah, that's right. Okay, good. Although for positive things, you kind of need to, yeah, well, I'll get to that. Yeah. Okay, and so, okay, so continuing, so I told you this model is going to kind of help us give these symbols life. So this, I've described what the pi does. I also need to tell you, I need to also prescribe base point change maps. So these are gammas, which are just like, well, they're playing the same role as the gamma I introduced on the earlier page. And what they need to satisfy is they can allow you to write pi at one point in terms of pi at another point. And that's the same sort of behavior that the gamma on the other page had. Okay, it was a way of taking expansions centered at one point and rewriting them so that I can evaluate them at another point. And it also turns out to be a good idea to enforce that they have a certain type of group property that says if I transport from A to B and then from B to C, that's the same as going from A to C. So this at first seems a little bit abstract compared to this, right? So this is kind of definitely meaningful because I want to take these abstract objects and make them analytic. But what these maps are super important for is they're needed in order to look at how these jets depend on their base point. So this is needed to formulate the notion of modeledness. And so again, how you define the modeledness condition for these jets is you take a jet at one point, then you take the jet's value at another point, and then you parallel transport. You take the difference, that's a linear, that's another jet, and then in that jet, each term should vanish at a rate proportional to the, well, not proportional, but governed by the degree of the monomial it's multiplying. Okay, so it's kind of, essentially, it looks like the same sort of definition. All right, so now I just want to quickly go on and talk about the rest of the theory. So upon fixing a model, we have a space of model jets, and the idea is that since I've given you some information on how, so if I have rules for how to multiply these monomials, so if I have rules for combining trees, just like we have rules for combining powers of x, and if I also tell you how to think about integration on these monomials, then both of these operations are inherited by the space of jets. Okay? And so that means, so here is this space of special distributions, in a sense, that I can think of as having good regularity. In particular, I can take products. And so then, on the space of jets, we can actually formulate the fixed point problem. Now, we call it an abstract fixed point problem because we're not looking for a solution, we're not really looking for a solution distribution at this point, we're looking for a solution jet. But it turns out that this fixed point problem is well posed because of these points. And so then we can find a solution. And so given a model, I'll write SA of Z as the solution to this abstract fixed point problem on the space of jets that you get from that model. Okay? Now, this is a super important point which motivated the definitions I gave before, which is that the space of jets we're working with is meaningful in that we can actually take these jets and reconstruct them into actual distributions.
Wait, maybe I missed something, but can you say how you multiply two jets?
Yeah, so the idea is that the multiplication is just pointwise, and there's a multiplication rule on the monomials. So you multiply jets like you multiply Taylor expansions. Okay. Good. Okay. And so there's also a reconstruction map which takes one of these families of local approximations and patches them together to create the object that is described by those local approximations. And so the key idea, which relates to this thing about thinking about rough objects as regular is that I can think about alpha here as being positive. That is to say that I can think about the local expansions as approximating my object to positive order, but I can then think about the actual object itself classically as being very rough. So to live in a Holder Bessov space of negative regularity, which I haven't defined, but if you look at the C beta spaces for beta negative, these are spaces of distributions. Okay. So the full definition of a model, which I haven't put up here, I've just told you the roles played by its various components. The full space involves a family of analytic and algebraic constraints. And so the space of models is one that is at first maybe hard to kind of parameterize explicitly. So it's a nonlinear metric space. So one important condition, which sort of relates a little bit to Malik's question before, is that we enforce this thing called a homogeneity bound, which is to say that if I take one of these monomials and I make it real, centered at, if I give it life centered about z with pi z, and then I evaluate it, if I use it to act on some approximate identity centered at z at scale lambda, then this should vanish or should satisfy an upper bound of lambda to the power degree of the monomial. Okay? So here, you should just think about this as lambda goes to 0, this becomes a delta function centered at z. So this thing is doing something like trying to evaluate it pointwise. So you can think about it as a family of L1 scaled modifiers centered at z. And so I want this bound uniform for small lambda. So one thing is if tau's of negative degree, then I'm allowing this thing to blow up, which makes sense because you're trying to evaluate a kind of distributional object at a point. But if tau is of positive order, then I actually expect this to vanish. And so this thing this thing will require us to implement some non-trivial z dependence on this pi z. Because if you just think about a regular object, if you think about an object that has some positive regularity, and then you just act on it on some approximate identity based on the points, and you send that to a delta function, you don't expect the result to vanish in general. So the idea is that this pi z needs to incorporate a sort of recentering procedure. So it needs to this is kind of related to how for x, if you kind of evaluate the blue x at some space-time point, or some space point x, you want to kind of center it about x. So we're going to have to do the same thing for the various random trees that these symbols correspond to. So in some sense, we have to kind of think when we have trees of positive regularity, or positive order, we want to somehow work with the increments of these trees rather than the trees themselves. And the way that you perform this recentering, I'm going to kind of describe the formalism a little bit later, it's going to be a little bit, it's going to be non-trivial, but I just want to mention here that one thing that makes defining models a little bit complicated is that there are strong constraints on how this map is allowed to depend on z, because the gamma incorporates somehow the z dependence of these maps. So finding out how to do this recentering in a way that gives you gammas with good properties takes a little bit of work. So this is why actually defining models takes a little bit of care. Okay. So I'll talk a little bit about this, so I'll come back to this in what follows. But I want to kind of go again to the main story. So what you win from all of this complexity is that the map that goes, if you kind of start with a model and then you solve the abstract fixed point problem in the space of model jets with respect to that model, and then you turn that solution jet into an honest distribution, a concrete object, then the map that you've constructed here is actually continuous. And so now we can sketch how you actually prove convergence of solutions to renormalized SPDE. So first, I want to kind of mention so I need to tell you something about why this concrete object is meaningful. Okay, so it's related to an abstract jet that solves a problem that looks like the problem we described earlier, but what does this object actually mean? Well, in order to get an intuition for that, first I want to say that let's think about one way to define a model. So if you fix what a model does on just the dots, or just you fix what the noise is, then it turns out that the only real degree of freedom you have is how to define the model on products of trees. And if you fix the noise to be a smoothened realization of space-time white noise, and then you enforce that these maps pi z are multiplicative, then actually that completely determines the model. And that gives you, so I'm calling the model that's specified by those criterion as Z super zeta sub epsilon. So then if you go through this whole construction, starting with this model, then the concrete object that you get is actually meaningful. So it agrees with the classical solution given by the non-renormalized modified equation. Now, okay, so now we want to control the epsilon goes to 0 limit. So naively what you'd like to say is, okay, well now I just send epsilon goes to 0, and then I see that these guys converge if I can show that the corresponding models here converge, right? So that's just using this continuity that I described above. So it turns out that, okay, so in practice, these models, any type of convergence that you get is going to be probabilistic. And in order to show that models converge, the hard part is to show uniform bounds of this type. So moment bounds that, so this is, uniform in lambda and epsilon. So you want uniform bounds in epsilon and lambda of the model on a tree applied to some approximate identity at some scale lambda. And you want these moment bounds to have the right type of scaling with respect to the degree of the symbol. And so what you'll see is that if you just take this multiplicative model, it's not going to satisfy this bound. So that's the kind of formulation of how in the theory of regularity structures we see the divergence of perturbation theory. We see that the multiplicative models don't converge. And that sort of makes sense. Sorry, there should be a 3 here. But what you'd expect is if you want to make this an analytic object, then you wouldn't want to just define it as the cube of just the single stick, but you'd actually want to construct some sort of Hermite polynomial.
Okay, so you have two UV scales here, the lambda and the epsilon, and
That's right. So you want uniform bounds in both.
do the limits commute when you take both to 0? Or is it something?
Well, I mean, you don't, in a certain sense, the lambda goes to 0 thing, the lambda goes to 0 doesn't really, this lambda kind of indexes a number, right? Not a model. So this number is going to blow up as lambda goes to 0. So I think about lambda as kind of a running effective scale. That's right. But the limit is only going to be in epsilon. Okay. So what's the task? Well, so these multiplicative models are not going to converge. But what one has to do is you have to kind of define, you have to, in a sense, mess with the definition of products like we did here. So you have to kind of design a model a little bit differently, so renormalize it in a way where the new renormalized lifts converge. And then if you can show that you have a probabilistically convergent sequence of models, then you know that the concrete objects that you build from those models, which somehow correspond to the abstract solution problem, also converge in probability. But then you're not quite done. So because of how we incorporate renormalization at the level of models, it's not immediately clear that this concrete object that you get actually satisfies a renormalized equation. So that's the last thing that you need to check, that this thing actually satisfies a kind of concrete renormalized equation. All right, and I can kind of say a little bit about why it's not obvious in this framework later, if there are questions. Okay, so now I just want to describe how the theory developed. So, of course, it all started with Heirer's paper, A Theory of Regularity Structures, which gave a scheme for describing the space of models, the space of model jets, how to pose and solve these abstract fixed point problems, and how to show that modeledness is the right condition in that a model jet can be reconstructed to a concrete object. So we kind of consider this the sort of deterministic theory of kind of understanding, the space of models and model jets. So this part of the story was done in a kind of very robust equation-independent way in the first paper. But then the other steps of the argument, which were showing that you can renormalize models to make them probabilistically convergent, and then showing that they satisfy, these renormalized models give you concrete objects that satisfy renormalized equations. Both of these steps were also kind of investigated in this paper, but were done maybe in a little bit more of an ad hoc way, just for specific equations. And so when people applied this machinery to other equations, they sort of had to figure this stuff out by hand. So then the next development is this paper, The Algebraic Renormalization of Regularity Structures by Brunet, Herer, and Zambati. And so here, what was done is really parametrizing the space of models. So to kind of give you a really rich cookbook, which gives you explicit ways to construct models. So this basically tells you, this gives you the kind of freedom to define renormalized models, because otherwise the nonlinearity of the space actually made defining models a little bit difficult. Okay, and then the third paper here is so joint work by myself and Martin Herer, which shows you that if you pick an appropriate sequence of renormalized models, you get probabilistic convergence. So it's sort of it's a kind of generic BPHZ theorem. So it tells you basically, it proves that these random trees converge once they're appropriately renormalized for any sort of equation that fits into the framework of the theory of regularity structures. And so in the last 15 minutes, I'll kind of describe that story. But then the kind of final piece, which is work with Yvonne Brunet, Ilya Shevarev, and Martin Herer, is to show how basically each of the recipes that were given in the second paper act on the level of the equation. So this gives explicit identifications of the renormalized equation, and it does so. Okay, so people definitely, of course, you know how to do this in perturbative quantum field theory by hand, but this gives a nice algebraic description of how you renormalize. It basically, so the renormalizations here are parameterized by a certain Lie group, and it gives you an action of that Lie group on the space of equations. It tells you how it actually renormalizes the equation. And this has turned out to actually, Yvonne will maybe talk about this a bit more. This has turned out to be useful in understanding how to renormalize when you have symmetry constraints as well. So analogs of word identities and so on.
Does your analytic BPH theorem now enable you to tackle renormalizable theory?
No. So this everything here, I mean, the deterministic machinery, yeah, so this is sort of like a perturbative input. So in some, I mean, yeah, so there are aspects of it that work for trees that appear in just renormalizable theories, but the whole story as a whole breaks down. And it breaks down because this special space of distributions is no longer the one where you can find the fixed point problem to the solution, right? So we can't assume that things are locally given by perturbation theory in the same way. So the whole sort of formalism breaks down in the just renormalizable case. Okay, good. Okay, so now I want to talk about this third work, which is this on the probabilistic convergence of models. And so the theorem is, it's kind of a type of stochastic continuity that is the counterpart of the pathwise continuity of the first paper. So it tells you that if you give me a sequence of random driving noises, then there's a way to lift them up into models so that if you have probabilistic convergence of the driving noises, you have probabilistic convergence of the corresponding random models. And so we call it BPHZ renormalization because it really does implement the Zimmerman-Forrest formula. So it generalizes in bounds that can be found in Hare-Quastel, but it's kind of where it kind of draws from, or its lineage sort of is by this work by Feldman, Mangyen, Rivesot, and Senior in '85, which is sort of a position space. It's a kind of position space scheme for bounds on amplitudes when you do the Zimmerman-Forrest formula. So I'll describe a little bit of those ideas in the very end. What I want to say just about new aspects of our analysis, okay, so the thing is that convergence of perturbation theory doesn't give you automatically convergence constructively, right? So you need to control a little bit, you need to control more than just the same type of perturbative diagrams that you see in quantum field theory. There's this kind of secondary type of recentering that we see in this analysis. So we need to get bounds that have the right sort of lambda dependence. And that's crucial to get convergence in the space of models. So that's kind of the key new thing that we need to do. Additionally, we also allow for non-Gaussian noise. So we kind of work with Feynman hypergraphs where you have cumulants instead of just edges. Okay, so I just wanted to write down a kind of formula that you see. So this special renormalized lift, again, is called the BPHZ renormalized lift. So the Zimmerman-Forrest formula tells you that if you're going to kind of renormalize some diagram, then you can write explicitly the renormalization prescription as a sum over forests of divergent substructures. So here, for the BPHZ lift, you have to sum over the forests of divergent substructures, but there's a second type of renormalization which is corresponding to this recentering, which we call cuts. So there's kind of there's a double forest formula when you're, or a double sum when you're looking at the renormalized models. And so here you should think about this as some counter term associated to a forest in a set of cuts, and this is just the quotient object that's left over. So let me actually draw some pictures to describe what this looks like. Okay, so here I've drawn a random tree. Okay, so this is kind of, this is not an algebraic object. This is actually corresponding to a multilinear functional of the space-time white noise. I've made the solid circles hollow just to make them stand out some. And so forests are collections of divergent substructures, right? So here, if you want to renormalize this forest, you extract both of them, and then the counter term associated to each of them is just their expectation. And so by stationarity, I can evaluate the tree at 0. So the term that comes in that formula for this forest is this one. And here I've put this red circle here to indicate the actual argument of the tree that's left over, right? So I'm renormalizing random trees to get new random trees, but these things are actually still space-time distributions. So they take a space-time argument, which is where this red guy is. Okay, and so then you also have nested divergences and overlapping divergences, which require you to kind of do some combinatorics on these forests. But here's a case where you have nested divergences. Okay, what's the cut? How did the cuts appear? Well, here I was looking at the model centered at 0. So in order to get the right behavior, in order to get the right dependence on the base point here, in order to get bounds that behave in the right way in lambda, you also need to sum over all ways to cut off subtrees of positive homogeneity or positive degree. So here what you should imagine is this tree and this tree have positive degree, and so then I'm allowed to chop off their trunks. And so this is the quotient object left over, and then this is the counter term. And so in some sense, this is a pathwise counter term. It's not a probabilistic counter term. And this sort of renormalization is something that's internal to the theory, but it is important for us in order to operate in the space of models. And so then in the end, you're going to perform a kind of sum over all forests and all cuts. And then, okay, you have the old problem of overlapping probabilistic divergences, but you also have problems about basically there being cuts in the same places where you want to do a probabilistic renormalization. So you have a new overlap phenomenon as well.
But in DPHZ, all this overlapping stuff becomes important for the renormalizable case.
Well, yeah, so I mean, in some sense, what you'd want to do, so there what you want to do is kind of do this effective expansion, right? So that you kind of bypass the issue of overlapping divergences completely.
No, but I'm saying you're dealing essentially with the subcritical case.
Mm-hmm.
Why do you have so many overlaps?
We can have overlaps even in the super renormalizable case. Yeah, I mean, it doesn't happen for 5.4, but it happens for other models. Yeah. Okay. Okay. And so here, okay, so now I want to just describe what the multiscale analysis looks like. So here I've written out the square of a model applied to some tree acting on some approximate identity. So these green lines represent the approximate identity, and then here are the trees, and so the red points were the arguments for the trees, and I've indicated these green lines. So again, in these pictures, the lines represent kernels. So now these green lines represent the kernel corresponding to the test function, which is, or the approximate identity, which you think about as pinned down at 0. And so then when you take an expectation, what you want to do is, okay, so if this is a Gaussian noise, then you can use Wick's rule to introduce contractions between the noises. So this is one sort of contraction that you see. And so these squiggly lines correspond to covariances. And so this is one sort of contraction that you can see when you're calculating the expectation of something like this. So this is how you see the graphs start appearing. And this notation, of course, is just some notation for an integral, right? So here, these black dots, you should think about them as representing position variables in space-time, which I'm going to integrate over. All right. So now what you want to do is, because maybe I'll try to do this quickly, is you want to kind of do multiscale analysis for this. And so how the best way to estimate this integral is, as was said before, a combination of kind of L1 bounds and L infinity bounds. And so how you organize that is, one way to proceed is to split up your integration domain into lots of little regions governed by the relative separations of the space-time points. So here, I'm summing over binary trees where the leaves are identified with the variables that I'm integrating over. And the binary trees are giving me information about the relative differences, relative distances between the various points. So here I've introduced, so here this curly T is the tree, T circle is the inner nodes of this tree. And so I'm summing over trees along with ways of putting numbers down on all of these blue nodes, where I enforce that the numbers increase as you go down the tree. And you should think about the number at a specific node as telling me that the distance between this point and this point is of the order 2 to the minus 216. Mm-hmm.
So the reason you don't have a triple fusion, is it because it measures 0?
That's right. You can set things up so that you don't see it. Yeah. I mean, this is kind of an annulus. It's not a circle. So you have a little bit of room. Okay. And so then what I want to do is I want to estimate. So this tree with the numbers specifies a domain. And then I want to estimate the integral on this domain. So then if I take one slice, it's just the volume of the region I can estimate it with a volume bound times a supremum bound. And so this is just kind of a spanning tree type argument. And then this is, to find the supremum bound, you just look at the various singularities of the kernels. The punchline is that you can write this as some factor that is given by a product over these blue nodes times some to the 2 to the power some weight associated to each blue node times the scale of that blue node. Okay, and so then you need to kind of sum over all the scales. So I'll end here. And so it turns out that, okay, so as you do in kind of bounding graphs, you want to kind of sum over the scales from the children in. But what's new here is that you don't sum to the kind of the root of this tree. You sum over the kind of first common ancestor of all the test functions in the base point, which tells you a certain type of running scale. And so then these positive cuts are what you need to do in order to guarantee that you can sum to this scale as opposed to this scale. Okay, but that's just kind of a bit quick. I think I need to end there. Okay.
Thanks a lot for that talk. Are there questions? No questions.
I mean,
Yeah.
sorry, I mean, if you only sum up to the scale, to this pink scale, why do you need the rest of the tree?
Okay, well,
Everything that is hooked to something above it.
that's right.
What role does it play then?
Well, this is kind of a way of describing the first bound when we do this estimate of this volume times suprema bound at the first scale, and we haven't integrated any variables. So this is kind of what we start out with when we're kind of estimating this integral, and then you eliminate these.
Ah, okay.
That's right. Yes. And so renormalization is just done in order to guarantee that you have the summability needed to eliminate these.
This was another way of saying it. I mean, you have things of positive degree, and so just because you are the larger scale doesn't mean you're smaller. You can actually also be bigger. So you need to make sure that the larger scale is really
It's there.
smaller rather
Yeah.
than bigger.
So
If
Malik,
you draw it and then you can erase it.
So I'm familiar with how to do BPHD in orderly Feynman diagrams because I have the full diagram, so I see what is divergent subgraph. But so am I correct in assuming that what you guys are doing is kind of a renormalization beforehand, before even having the full diagram, you just have one half?
That's right. So I mean, there's a little bit of a jump that I didn't describe, which is that the renormalization is done at the level of trees before you actually take the expectation of the product. And so then you have to match that the renormalization of the trees does correspond to the renormalization of all the moment diagrams that appear. Now in some super renormalizable theories, that actually isn't the case and you can't treat those. So there's some theories or there's some equations where there are new divergences that appear between pairs of trees, but those kind of fall out of this framework. But for most cases, cases like 5.4 or all the cases that people are familiar with, renormalizing on the trees first and looking at the moment you can rewrite that as a renormalization of the moment directly.
so I think we're out of time, so further questions can certainly be in the coffee break, and let's thank Ajay again.